Hello everybody, this video clip is the third video clip for chapter 6 and we are in section 6.2 which is the mean value theorem. Actually it is not only the mean value theorem but it also its applications, okay, which is a lot of application. One of the application that you used to use it, okay, it is about the relative maximum and the relative minimum value of a function. So if we have a function f, okay, which is sending from the interval I to the real number r, okay, we are going to say that this f have a relative maximum, okay, if at at the point c inside that interval, if we can find the epsilon greater than 0 such that your f of x less than or equals to this value f at c, okay, for all x within this epsilon interval, okay, around this c. So it just simply means that if we talk about the relative maximum, okay, so for example this one is the c and you just go to the left of the c a little bit by epsilon and go to the right of c a little bit by epsilon, then you can see that the function value around close to this point, okay, it is less than or equals to a function value at the point C, okay, this one is the relative maximum. Of course, as you can see that the relative maximum can be the point like here as well, so it's look like a hill, okay. So if you talk about the function value around that hill, okay, it's going to be a little bit less than, right, okay, around that point will be less than the function value at this particular point f at c, okay. So for the relative minimum it's just the other way around, so it will be a valley like that, okay. So again same thing, that around this point, okay, the value of the function will be greater than or equals to a function value at this particular point where the relative minimum is occurred, okay. So let us looking at this theorem. The theorem, before we go into the mean value theorem, okay, we need to prove this one first. It says that if your f is a function from the interval I to a real number r, and you see it is the interior point of this interval, so it means that it is not at the end point, the left end or the right end. And if your f has a relative extremum, then your f is not differentiable at c, or your f prime at c is 0. If you can, if you remember, then actually this one, the f prime at c equals to 0, this c is called the what? Is called the critical value, remember, in your math one, okay. However, actually the critical value, you got two kinds, okay. The first kind is that when your derivative equals to 0, and the second kind is that when your derivative does not exist at that point, okay. However, in our math one, usually we concentrate on this kind of critical value, all right. So to find the critical value is to find the good candidate to be your relative maximum or the relative minimum, okay. And if we talk about both of them together, we are going to use the word extremum, okay. So let us do the proof of this theorem, okay. To prove the P implies Q, but your Q it is in terms of OR, okay. Sometimes it will be more difficult if we do it directly. So we are going to use the contrapositive, okay, of this statement, okay. By contrapositive, we are going to prove negative Q implies negative P, okay, and the negate or the negative of your Q in terms of OR, it becomes the N, okay. So what we are going to assume, we are going to assume that your f is differentiable, so it's a negative of your f that is not differentiable, right? So this one is differentiable, okay, at c, and okay, instead of or we have and of course your f prime at c is not equals to 0, so it's the negate of your f prime at c equals to 0. So I mean immediately you got two cases, right? So the first case, your f prime at c may be positive, okay? So it means that this limit as your x goes to c of the quotient fx subtract your fc divided by x minus c will be positive, okay? So if this limit is positive, then by the theorem in chapter 5, you can find a neighborhood epsilon of c, okay, so that your quotient fx minus fc over x minus c, it is greater than 0 for all x inside this epsilon neighborhood around this point c, okay, but of course it must be in the domain I as well, okay. However, it can be excluded the c because this one is talking about only the limit, all right. So I mean because your this one is a quotient, right? You can just simply multiply, is it? However, if you want to multiply, you need to make sure that your x minus c is positive or negative, right? So it means that if your x, it is inside the interval c to c plus epsilon, okay, then what does this mean? Then your x minus c, because right now your c is right here, your c plus epsilon is right there, and your x is the point on the right of your c, right? So it means that your x minus c is positive, and it implies that your fx minus fc is also greater than 0, okay. So it means that your f of x will be greater than your f of c, okay. So of course f is not this one, your f at c is not a relative maximum, right? Because on the right hand side, the value on the right hand side, it is greater than, okay. And if your x, it is in this side of the neighborhood, okay, on the left hand side of your c, okay, so right here your c minus epsilon, and your x is right there, then it means that your x minus c, it is negative, and your f of x minus f of c has to be negative as well, right? In order for your quotient to be positive, okay. So it means that your f of x will be less than your f of c, okay. So it means that your f at c is again, because your there's a point I'm sorry, there's a value, okay, that is less than this f at c, okay, the value of f at this particular point c. So this one cannot be a relative minimum, right? So it means that your f has no relative extremum at the point c, which is the negate of your p, right? Because the p saying that your f has a relative extremum, and we can prove that at the end. I mean, assume your negate of q, then we got a negate of p, which is f has no relative extremum at this particular point c. Okay, of course we have another case, okay, where your f prime at c is negative. Okay, so a similar argument, we can use the same argument but just adjust a little bit. For example, this neighborhood, instead of positive, it will be negative, something like that. But this one, you can show that your f has no relative extremum as well at this point C. Okay, so this theorem just saying that if you are going to find the relative extremum, you should look at the point C in the domain such that your f is not differentiable or your f prime equals to 0. These two kind of point will be a good candidate, which we usually call a critical value of your function f. Okay, so now we are ready to prove the so-called row theorem. Okay, and this row theorem is something that we can use to prove the mean value theorem easily. Okay, the row theorem saying that if your f is continuous over the closed interval and your f also differentiable, okay, on this open interval a and b, and your f at a, your f at b are the same value and the value is 0, then you can find the c, okay, within this interval open a b such that the f prime c equals to 0, or you can say that we can find the point c where at this point we have the horizontal tangent, right, the horizontal tangent. So basically what we're talking about is that if we have this kind of interval AB and your f, okay, y equals to f of x has this kind of curve like that, okay, which is continuous and also differentiable, you can find a point C, okay, where the tangent line is horizontal, and from this picture we actually can find several places here, there, okay, and there, okay, where your horizontal, I mean the tangent is horizontal and the derivative at those particular point equals to 0. Okay, so by existence, okay, it doesn't mean that you got only one point, okay, you may have several points, okay, as well. So let us do the proof. All right, so of course if your f is all 0, okay, at the first place along this interval close a to b, then of course your f prime will become 0 for x inside this open interval a and b, and the theorem is, I mean, established at once. Okay, so let us assume, okay, that your f is not 0 at some point in this domain, okay, at some point x0 in this domain, okay, and we want it to be inside, because don't forget that another assumption is that the left hand side and the right hand side, the value of the function f is 0 already. That's the assumption, right? So because your f prime is not 0, so we actually got two cases. So the first case is that if your f at x0 is positive, okay, so by the max and the min theorem in chapter 5, have you forget, okay, it says that if you have a continuous function over a closed interval, then you always have max and min value inside that interval. Okay, so by this one, your f attain the maximum value inside. Okay, so suppose that your c, okay, is where your f attain its maximum. So suppose that your c is in AB such that this one, it is bigger than, larger than each and every value of f, okay, inside this closed interval AB. Okay, so of course, x0 is one of the point in this interval, right? So in particular, what we have is that your fc will be greater than or equals to your f at x0, and this one is strictly positive, right? Okay, so of course, because your f at a and your f at b is 0, so it means that your c is not a and your c is not b. So it means that actually your c at the beginning, it is inside a closed interval, it is actually inside the open interval. Okay, and when it is inside the open interval, we have another assumption that your f is differentiable inside this open interval a and b. So your f prime at c exists. Okay, so by the previous theorem 6.2.2, okay, it is saying that, okay, let we go back a little bit. It's saying that if your f has a relative extremum, then either your f is not continuous or your f prime is 0, but we already saying that your f is differentiable at this particular point, right? What we have assumed, okay, your f prime exists at this particular point. So by this theorem, another case can happen is that your f prime at c must be 0. Okay, right? And of course, for another case, if your f at x0 is negative, then you may try to use this argument to prove it by yourself. So this one will be left as the exercise, okay, for you to do. Okay, all right, and just apply the previous theorem to conclude that your f prime at the particular point c, okay, it equals to 0. Okay, so now we are ready to establish the mean value theorem. Okay, and the mean value theorem, it is actually the row theorem in the version that you rotate your curve a little bit, okay, by saying that if you have your f like this, okay, this is y equals to f of x, which is again continuous, and also be able to find a derivative at each and every point inside the interval from a to b. Okay, then if you find the secant line, okay, connecting the point AFA and BFB, you can find the point inside this interval, open interval AB, so that the tangent line will be parallel to this secant line. Okay, and again, we may be able to find several tangent line that it is parallel to the secant line over there, okay, connecting AFA and BFB. All right, okay, so this is the geometric speaking, okay. So let's look at the statement. It's saying that your f is continuous, as I told you, on the closed interval, and your f is also differentiable on the open interval. Then we can find a c, okay. For example, this one can be your c, okay, in this open interval, so that your fb minus fa equals to f prime c b minus a, or you can say that your slope of the tangent line equals to the slope of the secant line connecting AFA BFB, okay. So of course, as I mean, from the Rolle theorem, as we told you that we have this kind of curve instead, right? Okay, so at A and B they are the same value, which are 0, right? Both of them attain a 0 value over here, so you can find the horizontal tangent, which is actually this horizontal tangent. It is the slope of the tangent. It is actually parallel to the x-axis, which is the straight line that passing through these 2 points as well, right? AFA and BFB, okay. So we are going to use the Rolle theorem to prove this one. All right, so let us do the proof. Of course, we already assume that your f is continuous on the closed interval and also differentiable on the open interval from A to B, okay. And you are going to define another function that satisfies the Rolle theorem. So it is from the closed interval AB to R, so that your phi of x equals to f of x minus f of a, and then minus fb fa over b minus a multiplied by x minus a, okay. So this part is actually the one that you need here, okay, and then the rest we just attached so that this phi will satisfy the Rolle theorem, okay. So immediately you can say that if you replace your x by a, this one cancelled. If you replace your x by a, this one also cancel, so you got all 0 at once. And if you replace your x by b, okay, by b, this one cancel first, and then the negative will distribute inside, so your fb cancel as well as your fa, okay. So phi at b is also 0. All right, and of course your phi is continuous, right, on the closed interval AB, because it is constructed by a continuous function and a polynomial, okay. And it is of course differentiable because it is constructed from a differentiable function and again a polynomial, so it is differentiable on the open interval AB. So by the Rolle theorem for this function phi, okay, there exists a point C in an open interval such that your phi prime at C is 0, okay. However, can you calculate the derivative of this function phi, okay, phi prime at arbitrary point x? It is f prime at x, right? And then a derivative of the constant, it becomes 0, and a derivative of the constant multiply, it is only fb fa over b minus a, and the derivative go to that polynomial, right, which is 1 minus 0. So this one becomes like f prime x minus this quotient, is it b minus a, okay, and your phi prime at c will be 0, right? So this one, it is f prime at c minus this quotient, okay, fb minus fa over b minus a, all right, and it is equals to 0. So you got your function, you got your equation as required, all right, which is the equation that you need for the mean value theorem. We get, okay. So now let's look at some application of the mean value theorem. The first application is through this example, okay. This example is just simply saying that your e to the x, the exponential, always larger than the polynomial, okay, and this one is a polynomial of degree 1, okay. So to do this, we actually need to let your if your f of x equals to the e to the x, we need to give this information first that a derivative, it is equals to e to the x itself, okay. For all x in a real number. Actually, you know it from your math one. However, up to this point, we still cannot prove that the derivative of the exponential function, it is actually the exponential itself, okay. So this one, we just let it first that this is the derivative of e to the x, all right. So we let x be an arbitrary real number, okay, because we need to prove it for all real number x, okay. We need to set your f, okay, to be e to the x, and we are going to separate into several cases, okay. So for the first case, which is the easiest one, is when your x is 0. So we know that e to the 0 is simply a 1, which is greater than or equals to 1 plus 0, which is your 1 plus x, and your x is 0, okay. So this one is the case where your equality occur, okay. Now for the next case, if your x is positive, okay, then by the mean value theorem, which we are going to abbreviate by MVT, there exists c in this interval from 0 to x, okay, because right now as your x is positive number, then your exponential function, it is actually continuous in the closed interval 0 to that x, and also can find a derivative inside the open interval 0 to x, okay. So we can find this c in this open interval, you see, such that your f of x minus f at 0 equals to f prime at c multiplied by x minus 0. So your f of x, it is actually e to the x. Your f at 0, it is 1. Your f prime at c, it is e to the c, and then multiplied by x, okay. So it means that you got e to the x, because you need your left hand side to be only e to the x, right, equals to e to the c times x plus 1. So you almost got what you want. However, this one is the thing that is too much, right? We don't really need this e to the c. However, because your c, it is positive, okay, because your c is positive, then it means that your e to the positive number is always greater than 1, right? Because e to the 0, it is equals to 1. So e to the c, when you're an e, your e is an increasing function, right? So as your c getting larger than 0, your e to the c will greater than a function value at the 0 point. Okay, so this one is greater than 1. It means that this one can be greater than x plus 1. Okay, but if it is greater than, you can say it is greater or equal. Okay, but this one I'll keep it as greater. All right. Of course, by the second, for the second case, if your x is negative, by the same old theorem, by the mean value theorem, we got a point D, okay, inside this interval again from x to 0, because right now your x is on the left of your 0, okay, so that your f at x minus f at 0 equals to f prime at d and then x minus 0. So your f at x, it is e to the x, and your f at 0 again, it is 1, so it will be equals to e to the d x plus 1. Okay, however, as your x less than 0, then it means that your, again, it is the same thing, that your e to the d, okay, because again your e to the 0 is 1 and your d is less than, right? So your e to the d is actually less than 1. Okay, however, your x is negative, right? Okay, your x is negative and your e to the d is less than 1. As you multiply, okay, you are going to, as you multiply this one by x, we have x e to the power d, right? It is, you cannot say less than, right? Because this x is negative, so it must be greater than. Okay, so this one will be greater than e to the d, greater than x plus 1. Okay, again, this one is strictly greater than. All right, so what we have from case x equals to 0, x is positive, or x is negative, we can conclude that, okay, your e to the x, it is actually greater than or equals to 1 plus x for all real number x, where the equality, okay, this one in math, even though greater than or equal actually can, sometimes it can be replaced. However, if we really put equal sign, we really need to know that the equality has the case that can occur. Okay, so this one, the equality occur, okay, whenever your x is 0. Okay, all right, so this one can be one of the immediate application of your mean value theorem. Another application of the mean value theorem, it is in terms of these two theorem like this. Okay, the first one, if your f is continuous on the closed interval AB and differentiable on the open interval AB, and your f prime is all 0 inside this open interval AB, then it means that your f is actually a constant function in the closed interval AB. Okay, this one actually is something that you use it, okay, without realize that you can prove it as well using the mean value theorem. Okay, so let's do the proof of the theorem first, and then later on we are going to talk about the corollary. Okay, so this one we are going to claim that because it is or constant, right? It is a constant over this closed interval, so it means that your f of x should be equals to the function value at sum of the either left end or right end so we just use the left end, okay, for all x inside this interval AB, okay, inclusive, right? So we let your x inside this closed interval A to B, and of course, so this one, your x is greater than or equals to A, right? By the mean value theorem, okay, the mean value theorem, over this interval from A to X, okay. To be exact, let me do this one over the open A and close B. Why is that? Because your f at A, of course, already it will be equals to, f at A, right, as you replace your x by A. So we can just move a little bit away from the A. So let me remove this one. So we are going to use the mean value theorem over this closed interval, okay. There is a point C inside the open interval from A to X, such that your f of x minus f at A, the left end and the right end, equals to a derivative at this point C multiplied by x minus A, okay. And this one, because your f prime at x, it is 0 for all x inside the interval, the open interval A to B, and your C is one of the element in this open interval, right? So this one equals to 0. So it means that the equation becomes f of x equals to f of A, okay, whenever you are x, it is in this open A and close B, okay. And if you talk about x equals to A, as we told you that it just simply the same, right, because you're talking about the same point. Are we all right? So we have this theory, okay. How about the corollary? Okay, the corollary says that if your f prime and g prime actually the same value, okay, for all x inside this open interval, then it means that your f and your g, okay, they are almost equal, but they just differ by a constant k, okay. So to prove a corollary 6.2.6, okay, we just define another function, right? Because of course, if you look at the equation, you can link this equation with the one equals to 0 by letting h, okay, from the closed interval AB to R, such that your h, it is simply f of x minus g of x, right? So it means that your h is continuous, your h prime exists over the open interval, and your h prime x, which is f prime, okay, minus g prime, because they are equal, so it is 0 for all x inside this open interval from A to B. So by the theorem 6.2.5, okay, we know that your h equals to a constant, right? So let's say that it is a constant k, okay, constant k. So it means that your f of x minus g of x equals to this k. So your f of x equals to g of x at this k, okay. So differ between the f and the g is by this constant k, okay. So this one, it is a constant for all x within this closed interval A to B. So this one as well, it is for all x within this closed interval from A to B, okay. So let us stop this video clip right now. We still have some further application of the mean value theorem to talk about, okay, and then we are going to see you on the next video clip with more applications. See you.